So this is our speaker today, Dr. Randy Shumaker, who I've known for over a decade. And as you can tell, his degrees are from Penn. He's a strong Penn person here. Randy's had an amazing background. He is going to be talking to us today on human-robot interaction. He used to be the director of the Lab for Artificial Intelligence at the Naval Research Laboratory. So, incredible background in artificial intelligence, computer science. He now directs the Institute for Simulation and Training at University of Central Florida. Well, you know, Florida, Orlando, you've got all the video game companies, you've got all the flight simulation companies, because Orlando used to be a major aerospace hub. We think of California as being a major aerospace development hub, but Orlando was one of the first. And the Army actually moved. He's got, what, you're 3 buildings now?
Yeah, 3 buildings.
3 buildings for the IST, 250 people working on all things related to human-centric computing and simulation. And the Army moved and set up one of their facilities just to take advantage of the fantastic team that Randy has attracted and maintained over the years.
Scary.
It is, and you're such a role model for me on how you do that. So Randy's going to be talking to us on human-robot collaboration. Please welcome our Donuts and Disaster speaker.
Very good turnout here. Our engineering department, which is 8,000 students, fairly big, used to have a problem with people coming to seminars. People didn't come to seminars. So they changed the name of the seminar series to the mandatory seminar series. So the name alone, and they got better turnout, and they started taking roll too. So it became much more popular. So I'm happy to see so many people here. Some of the stuff you're going to see you may think is weird science, but you have to understand my background and the kind of thing we do. My institute does human-centric modeling and simulation. So we're interested in how people think, how teams behave, how people interact with gear, how they learn things. So we can wire you up and see what's going on in your head while you're learning something. And we've done a lot of work with the Army in operation of unmanned ground vehicles, new and improved now with aerial vehicles as part of that. The Army is very interested in that. The kinds of questions they ask are, well, how many vehicles can one person manage? What's the best kind of interface for this? How autonomous can you be? And so on. The project I'm going to talk about is the Robotics Cooperative Technology Alliance that the Army Research Lab funded. It's a collaboration among many universities doing lots of different things, the goal of which is teams of people and robots working together as opposed to people operating robots. And some of you may say, well, that's weird science. You're going to need AI. You're going to need all kinds of stuff. But the broader picture is human automation collaboration. So we also do a lot of work with NASA, and one of the big studies we have now is if somebody were going on a 3-year mission where you can only have 5 people, but you would need 10 crew members normally to do all the functions. Oh, by the way, the ground station is 45 radio minutes away, so they're not going to be much help. You're going to have to rely on the automation. And the automation is going to have to be very flexible, and it's going to actually have to collaborate with people. So don't think about, I'm going to be talking about robots, but the bigger picture is how do we collaborate with our gear as opposed to either having it fully automatic or operating things. And that's a step that needs to be taken in many cases. So as Robin said, my institute is 250 people, all kinds of weird people, lots of psychologists, computer scientists, roboticists, but also including people from theater, because they help us design scenarios and how to understand how to recognize behavior in humans and generate the analogs of human behavior in machines. And you'll see why that's important when we get into this. The machines need to be able to read what the humans are doing, and the humans, without detailed training, ought to be able to tell what the machine is doing too.
Hey, Randy, can you talk a little louder? We're getting more people further in the back.
Okay, well, maybe I'll even stand up.
We couldn't go to a bigger room, so
I will project more. So the Defense Science Board, some people have, and I didn't cause this to happen, but it says that human-robot interaction, natural language, multi-agent coordination will be good things. So this is my mandate. Actually, the program started 4 years before this, but that's okay. It's always nice to get, so perhaps we have influenced thought or we've been influenced by thought. But this is getting to be a very common thing. The Army has decided that 1/3 of their forces will be robotic within a few years. It's not going to happen real soon, but that's the plan. That the things that go out and disarm IEDs, there won't be a person operating controls. It'll be able to navigate to it and at least do some fundamental things by itself. What the Army found is that it's very dangerous to be an IED robot person because of line of sight. And if somebody that doesn't like you sees a robot turning out, they know that somebody has eyes on that because they're operating controls. And so who do they go after, the robot or the operator? So not a safe occupation, even the way it normally works. So anyway, this is our mandate. Natural user interface. Trust and confidence is a term that's been used here. How much do I understand how this works? Will I decide to distrust it at just the wrong time? Think of a lot of industrial accidents that happened because we turned off the safety feature. 3 Mile Island was exactly like that. But we didn't see that before. Reactors are shutting down. Let's stop from shutting down. And got to think about it. There's also overtrust. There was an L-1011 and lots of more recent ones where people trusted the autopilot completely. The L-1011 glided into the Everglades nice and smoothly while they were trying to troubleshoot a coffee heating problem. Because nobody noticed that the autopilot had disengaged. There's a lot of Airbus problems that have to do with understanding the automation and getting cross modalities. So where would we like to go? Currently, robots used by the Army, and this is focused on Army because they're the funders, so we just have to do that. They're operated and they work in isolated environments. We would like to have robots be able to collaborate. And what I mean by collaborate is work as a partner rather than just being operated. And I didn't see any eyebrows go up, but probably mental eyebrows are going up. You know, what the heck does that mean? I'm going to explain that. And we'd like these robots to be able to work in not sanitary places. We would like them to be able to work within a team and also in an ambient society. So right now, robots recognize humans only as obstacles to navigation. And we would like them to recognize those as agents within the system. Ultimately, the Army and others would like to have robots that can work within an inhabited area and not cause problems. So there are really questions about, does the robot understand what the social norms are? How closely can I approach somebody before they become concerned? How do I make the equivalent of eye contact so that they know that I see them and I'm not going to run into them? How fast can I move? How slowly should I go so that people feel comfortable in my presence? These are questions for many, many applications, for hospital, for home, but in particular working in inhabited areas, okay? So ambient society means there are other people that are not players in this. They just happen to be there. But we're going to change the way we think about performance to be from how the individual does or how the individual robot does to how the team performs. So sometimes the robot will be operating in a suboptimal way because it augments the overall performance of the team. And we think that's a very important feature. Characteristics from individual robots to teams. And what we mean by teams here is a mix of people and robots that could vary. That is, a squad for a fire team might be sometimes 4 robots and 2 people, or it might be 4 people and 1 robot, or it might be any combination of permutation and still be able to function as an effective unit. Maybe not exactly the way it would be all humans or all robots, but be able to have that flexibility. So if something happens to one of the vehicles, they would automatically fill in and perform whatever functions needed. No operator control unit. The goal of this was, can you build interfaces such that people naturally know how to make this work? And by naturally know, we mean speech, gesture, different kinds of affect. Now, obviously, there is going to be a control unit. There's going to be a master operator who has to do software upgrades and stuff like that. But it's not going to be anybody hands down and eyes down operating something. They're going to operate it in ways that are more natural for people. If you're going to operate in an ambient society and you're going to operate with people who are not trained to do these, they have to naturally know how to make signals that the robot will understand. And the robot needs to be able to generate signals, social signals, that people will understand. And examples will be given about that. Right now, robots consider things in their world as obstacles. So a trash can and a human standing there are the same thing to a robot. Something I have to avoid or run over if necessary. We would like the robot to be able to understand that there are agent players. My team, just people that happen to be there, and operate at a higher cognitive level than they have. So not just the physical world, but there's a social world they need to understand too. So a lot of weird science has to go into what does it mean to have a world model that includes cultural artifacts and human culture. So that's the goal. The Cooperative Technology Alliance has a lot of names that you would know. The way these work is it's universities and companies, and we each have a role in there. So Penn is there, that's always a good thing. And Carnegie Mellon and Florida A&M and Caltech, also other names you know. There's UCF. Who the heck are they? Well, UCF, 60,000 students. It is the second largest university in the country. It has 10,000 students of computer science and engineering. So it's one of the larger technical schools. It has 2,000 students of nursing and large physics department, large psychology. But people never remember that, so I'm going to give you a way to remember. Okay. I've tried to get them to change the name of the university to University of Florida, Orlando. So we'd be UFO. And everybody will remember that. But so far, UF has subjected it. Let us do that. So we stay there. But the reason we're there is because we have this peculiar role of the human side, modeling people, modeling how people interact with machines and so on. And that's the role that I would hope to play with some of you. And if you're interested in learning more, come and visit us or take a look at some of the stuff.
I'm a former Foster Miller employee.
Oh, very good.
And I had a very, very limited role with their challenge provided system.
All right, very good.
Very limited. But I wanted to point out, you should update this because it's Kinetic North America now.
Yeah. Well, this is the original logo.
Oh, it's okay.
From 4 years ago.
Anyway.
Also, you notice Boston Dynamics is here. They make Big Dog. They were bought by Google. And so Google owns Big Dog. Does that strike fear in your heart? Or
yes.
They're going to make you buy stuff or what? So 4 different thrusts with different universities, different combinations. So perception, the goal is to be able to have the robot organically be able to recognize stuff, not just transmit images, but to recognize stuff, put labels on. So a lot of work has gone into that at Carnegie Mellon, UPenn, and other places. Intelligence, how to plan, how to understand, be able to, in effect, understand the environment we're in and solve problems dynamically. I came out of the AI world, which is definitely a weird science world. 7 architectures have been tried in the last 4 years. So we think we're finally on the final architecture. Okay, so that's been a big problem. And more on that if you ask, because one of the issues is roboticists tend to want to build a cognitive system. We deal heavily in people, and we find that when you train people, the goal of it is to move everything out of the cognitive layer and down to reactive. So think about when you started driving a car, you had to think about everything, you know. How soon should I start to slow down? How fast should I be going? How do I turn the wheel? When you became proficient, you stopped thinking. It became automatic and freed up your mind for more important things, like talking on the phone and stuff like that. So this cognitive idea, I think, is a problem in that I think you can get very high-performing things without having a cognitive level. I submit to you the Dragonfly. It's a very high-performing aerial vehicle, avid hunter, great processing things, and as far as we know, it doesn't think very much. I think the brain is 20,000 neurons, something like that. So cognitive's good, but the goal in human training is to move things down the stack to free up the cognitive space, and that's one of the things that roboticists are finding now. Manipulation mobility. So these guys want to be able to go through that. So snake robots, millipede robots, all kinds of mobility and manipulation things. So arms for doing things. And then my area, human-robot interaction. We would like to have robots be able to function seamlessly in this architecture and be able to do things like this. You go over there, go behind the building, and let me know if you see anybody come out of the building. Just like that. So, this sounds great, right? People had problems thinking about this. The roboticists in particular had a problem thinking about, well, wait a second. Our goal has always been to make this autonomous. You turn it on and it performs all this stuff by itself, just amazes everybody around it. And we want it to not necessarily perform things by itself. We want it to be able to function as part of a group that's trying to solve a problem. So there have been a lot of people historically who said, oh yeah, we do teams of robots, okay? Well, typically it's one of two architectures. One is there's some God's eye view that controls all of them, and that's what they mean by a team. There's a central control, it's not a team. Or, from the other end, you've got multiple entities doing their thing at the same time in the same place, and they don't really interact as a team. They're just all doing their same thing. We want to go someplace in between, where they actually have cognitive capability, but also understand that if this guy's doing that, I don't need to do that, I can do something else. Or if that guy is getting in trouble, I may need to go over and help them. So that's true team-like, without a central control. The metaphor we've used is service animal. And it's a good way of thinking about it. It's a good way of telling very high-ranking people who don't understand any of this stuff how to think about it. So think of a sheepdog and a shepherd. The shepherd doesn't steer the dog with whistles and clicks. The shepherd says, I want the flock from there over to here. And they may give some commands, but mostly the dog is operating as an independent agent, or dogs collaborating. So it could be combinations of people and animals. Think of a seeing eye dog, okay? Does the blind person drive the seeing eye dog? Well, if they did, nothing would work. The blind person says, I want to go to the store, or I want to cross the street, or whatever. But the dog has responsibilities and has a high cognitive responsibility. If the visually impaired person wants to cross the street and there's a bus coming, the dog can refuse the command because the dog understands what we are trying to do. And one of them is not get run over by buses. So it's a metaphor that actually works in this case for several reasons. One, I think it's going to be a long time before we have human cognitive level in robots. Okay. And two, people naturally understand this. Almost anybody understands how they might work with an animal, how they might work with a hunting dog, how they might work with a drug dog, how they might work with this. And so if you plant that seed in their mind that you should think about this the way you would a service animal, they automatically understand that maybe it does understand gesture. Maybe it does understand that if I look a certain way, there may be something of interest over there. My institute has worked with teams for a very long time, 30 years, looking at large teams, small teams, multicultural teams, all kinds of teams, healthcare teams, crew resource management for FAA. We've had a very long-term contract with the FAA to look at these issues of coordination, and we're doing more in health. And a lot is known about how to train and how to select high-performing teams. Okay, it's called the Big Five. A little factoid that you may find of interest. High-performing teams communicate explicitly very little. Low-performing teams communicate a heck of a lot. So think talking, pointing, all kinds of stuff. Why do the high-performing teams communicate very little? Well, they're actually communicating quite a lot, but they don't need as many words because the high-performing team has things called mental models. They understand what the task at hand is. Everybody understands what we are trying to do. They understand what each individual is supposed to do in that task, and they can observe where they are in that. So high-performing teams might just have a nod of a head to pass a huge amount of information because what they're doing is activating part of that mental model, okay? Or a high-performing team might see that Dr. Murphy is heads down, very busy, and the thing that she's supposed to do next, she's not going to be able to do, so step in automatically and do that because it's good for the team. It may not be my job, but I can see that to achieve the end. So the Big Five are leadership. What does it mean to be in charge of that? Team orientation. The members of the team have to think about themselves as a team, not just a bunch of people that are hanging around together at the same place at the same time. Okay. Backup behavior is, okay, suppose something happens, what kinds of things am I authorized to do? What kinds of things should I do? And adaptability, the military term is, the best plans go to hell when the first shot is fired. Okay, well, the same thing happens when you're trying to do anything. Things happen you didn't anticipate, so you have to be able to adapt. And the mutual performance monitoring is key to that. I know not only what I'm doing, but I know what the other members of my team are doing in the overall plan of things. The term that's used for that is the shared mental models. You need closed-loop communication to make that work. And trust is very important here. Because you may know all this stuff, but if you don't believe that they're going to do the right thing, you will not get advantage of the high performance of the team. So you have to really trust. And there's a whole research thrust called trust and confidence in automation that people are looking at. How do people learn to trust the system? How do they learn to calibrate it correctly? Because overtrust is just as bad as undertrust. It's how to calibrate it important stuff. Here's what we do. Question?
Yeah. Can you go back to the previous chart, please? There's another application that comes to mind directly. You're talking about high-performance teams. It's like basketball.
Yes.
And the very highest-performing basketball teams know where they're at on the court. They'll, the point guard will even pass behind him without even looking because he knows.
That's a classic example. The blind pass is a perfect example of this high-performing team knowing where this person will be and when, and trusting that will happen.
And the experienced players have their mental models very well developed, and a team that are like either rookies or inexperienced players are still building their mental models or have much lower ones.
They do not. Yeah, exactly.
But there's also another level is with the levels of initiative. So that backup behavior, the team oriented, and mutual performance monitoring. You very rarely see performance monitoring. You never see backup behavior because that really requires initiative to allow. Most of the Army systems don't let you have, even if the system can see that the team, and it should step in, often handicap those very benign, but it's initiative. That would be bad because it'll grow up and kill Sarah Connor.
Well, so all the stuff that we said we wanted to do, you can't do without this. Okay. And if you want the robot to fit in the team, it better understand how human teams work. And I use understand advisedly here. It has to be able to function as if it has the mental model and so on. So our approach was we know how good human teams work. If we want the robots to be part of that team, the robots have to conform to human standards because we don't want to be training everybody how robots work or how this peculiar one works. Or a new model comes out, everybody's going to be retrained. We want the robot to understand at some level how the team works, how the human team works. So the Big Five is used as a model for what you have to put in the robot. So these are the key things the robot has to be able to do. It doesn't have to be able to do all the things that the human does, but this is what it has to do. Future performance monitoring. How does it know what's going on? So is this high bandwidth video going on all the time? Well, not necessarily, because the robot ought to be able to, by observation, see what other members of the team are doing, robotic and human. So performance monitoring might be, is everybody in the right place at the right time? So don't think about this just as a whole lot of radio communication. This could be an observational thing. My guy is looking really worried. That's a piece of information that a human would understand. Should the robot understand at some cognitive level that that's a potential problem? Situation assessment has to understand what's going on. In the military teams, what we do is there's a handbook of all this stuff. So you got coordinate search, you got bounded overwatch, you got all standardized procedures. If you put those procedures in a form that the robot can understand, by observation you can say, oh, I've been told we're doing bounding overwatch, and I've been assigned this role. You don't have to do a lot of explaining. It now has basically a script that says what that means, what I should do. In coordinate search, similarly. So they're standardized things that don't specify exactly what the robot's supposed to do, but do specify what has to happen. And if a human's performing one function and some function that's necessary is not being performed, the robot ought to be able to recognize that and deal with it. Adaptability, as Dr. Murphy says, that means robots going to have authority to make some kinds of decisions. So there has to be some flexibility so that it can do these things appropriately. So I'll give you a trivial example of that. One of the things we have as demonstration mission is go to the back of the building and let me know if anybody comes out. So that's the robot's assignment, navigate it back and alert if a human being appears out of the back of the building. Well, suppose on the way it finds somebody embedding an IED. Well, nobody told it to look for that, so just basically ignore that, work around it. Well, no, it should be an initiative thing. Well, this is something else that the person, they didn't ask me for this, but this could be of importance. And a little joke on the perception people, okay? The original command was go to the back of the building and let me know if somebody comes out the door. So that involves the robot having to recognize what the door is. So if somebody comes out a window, oh, well, that wasn't a door, so I don't have to say anything. Or suppose it's the hole in the wall, and they come out the hole in the wall. Oh, well, that's not the door. Either that, or I have to classify any orifice in the building as a door. Well, the psychologists use a different way. They talk about affordances. So you should just be able to say, I don't care what kind of orifice they come out of, okay? If they come out of the building, let me know. So it's not, I don't have to exhaustively label all the ways they come out or rappel down from the top. So that's been an actual discussion between perception people and the people in human-robot interaction. You really want to know what it's good for, not necessarily the name of it. Okay, so if the robot comes in a room and it's looking to see if any people are hiding, the perception people say, well, we'll label everything. Tables, chairs, there's a bookcase, and so on. And then we'll say, which things could a human hide behind? Well, bookcases, and so on. What we told them is, I don't care what the name of it is. I just want to know if it's big enough for somebody to hide behind. So it's a hiding place. So how you think about these problems and coordination between sensors and intelligence and purpose make a big difference. Yeah.
So qualities rather than
qualities. What's this good for? One of my early mentors was Rosanna Baichi. Okay. And at that time, when I was a student, she had a big research project to have vision recognize a chair. And that problem people are still probably working on, okay? So chair, it's a thing you can sit on. Could a trash can upside down be a chair? Well, yeah, okay. How about a box? How about this table? So the problem is putting a label on it is too specific. An easier question to answer is, does this thing have enough width and height to be suitable for somebody to put their butt on? And that's actually an easier question for perception than putting a label on it and saying that's a chair, because it might not be a chair. Maybe it's a trash can sometimes and a chair other times, or a table other times. So it's functionality. This team orientation is key, and we know a lot about teams. The Big Five at some level gets embedded in the robot and understands that it's a component in an overall system, not just an independent entity. So the goal is, this is our basic dog. Okay, this dog's not too smart. And we understand one-on-one teaming, and we do some one-on-one teaming with robots. In the case of the bomb robots, people super bond to these things. If the robot gets blown up, they take it back to the shop and say, I want you to fix Sam, not issue me another robot. They want him or her. So there's a lot of anthropomorphism that goes on. We want to take advantage of that rather than discourage it, because we like them to understand that this is a teammate, but not risk themselves to save that teammate. Yeah.
I've seen that go both ways. So has anybody looked at that a little deeper than the little letters back to the depot? Have they looked at the personality inventory?
Yeah, Peter Hancock has done that. He's a psychologist that does this kind of stuff.
What did he find? Is it based on personality, or is it a fairly universal? Fairly universal.
People bond with their stuff, and particularly if it's something that has saved their life or is a very, very important tool. People give their cars names.
But not everybody. That's been a dichotomy. Right.
Not everybody does, but they tend to think of it in some ways. They may not go as far as name it, but they say, oh, my car's really, really happy today. It's running smoothly, or it's a little uncomfortable today. So they may anthropomorphize it in more generalized ways. Not everybody does it. It's actually not a bad thing if you want to do the team stuff. Yeah, question.
Yeah, so when I worked at Foster Miller, I remember once one of their Talon robots was sent back. It had been in use in the Iraq theater, and it had been impact, I think, had been blown up by an IED, so it was sent back for repair. Then I just remember when it came in the back dock, the engineers treated it. I got the impression like it was a wounded soldier coming back. So this is the engineering team rather than the soldiers team. Nonetheless, though, it was like, this is a wounded guy. We got to fix him up and get him back out to the front again.
The more cognitive capability you put in these, the more flexible behavior, the more that's going to happen. So a lot of the IED robots are, very simple, straightforward, but it's a useful thing in the trust and confidence thing, to think about it in particular ways. It's a team member and so on. We don't want that to go too far, so there's a balance there that we haven't quite perfected yet. So dogs perform as a team. One of our longer term goals is to be able to have that dog equivalent to a robot. I'll show you some pictures of that. So these are the issues we're addressing. And I use UXVs here because the Army project was focused on ground vehicles. But we've done separate work for the Army that is, how do aerial vehicles and ground vehicles coordinate to solve a problem? How do they maintain a common picture and so on? So this is a generalized issue, and people use birds for hunting too. So that works too, but at a slightly different level because most birds aren't too smart, but dogs are smarter. So these are the things we want to do. We want to model the human relationship to this. We have a lot of experience in the entertainment industry. We have a lot of experience in how people bond to biomorphic things. We specifically chose not to do anthropomorphic for several reasons. One is there's too many joints and too complicated, and I don't think you need all that. The other is people get a false impression if it looks too good, it's not going to be performative. If it looks like a human, but it acts like a turtle, that causes a little bit of disconcert. So it should be by observation. You should be able to calibrate roughly what kinds of things it's capable of cognitively and otherwise. We also need to understand the people end of it. So there's been a lot of study of what will people accept, and how do you move these into things that people will accept readily. So what we have been doing, we do a lot of modeling simulation. Roboticists like to build a robot, go out in the field and test it, but that's really inefficient for the stuff we do, because what we want to do is say, here's how you should build it. Here's how it should look. Here's some of the functionality it should have. Here's what the brain should contain. So there's been some back and forth with that. So the kind of robots we're dealing with, they use 3 iMac minis as to computing. And strip everything out, it's just the bare board. But it's still limited in how much computing it can do on board. We want to look ahead and say, well, computing, we can get here a lot of computing power. Let's not limit ourselves to what you can put on board right now. Let's see what you could do and decide whether it's worth putting that computing power on board and see how that works. So we look at human, and here's my robot that's performing in the same role, doing the same thing a dog might. So we've done modeling of physical workspaces, so cultural places in strange lands, mostly in the Middle East. And we can run human subjects and ask them what they see, what they observe, how they might interact with these. We do the same thing with the robots. We have robot test beds where we use man behind the curtain. The robot really isn't that smart yet. There's somebody running this, but we want to understand how the people think about it. Did they recognize this? How do they interact with it? What sort of social signals make sense and how they do it? So we have test beds that are open source that you can get for doing this, for the human cultural side, but also for the robotic testbed side. So our simulation is human-centric. We assume that we will get simulations of the physical robot from somebody else. We don't do those, but we do the human side and the cognitive side. So the ultimate goal is communication. And among the things we've studied are vocabularies. How do people talk to each other? What's the standard terminology for these things? So I'll tell you a little bit about where we are in this process, and then open up for any kind of questions in any domain that might be appropriate. We have multiple tasks. We have H1 and H2, our 6.1 project, basic research and exploratory development project, that are companions. And those focus on team. So how do we encode in a mechanical form what it means to be a team member in human teams. And that's been almost entirely focused on military teams because they're handbooks of standard procedures. Soldiers get trained to do particular things in particular situations. So how do you encode that in a form that the machine can use so that it can, by observation, determine what's going on? So trivial example, my guys are going down the road and I'm the robot and I'm turning on, and suddenly they go off the side of the road and hide. Nobody told me what to do. What should I do? So it should recognize that the situation has emerged and take the cue that there's some reason why these guys have changed. Or I'm observing a situation and I see them moving from cover to cover. That's a clue of what's going on. Nobody may have told me directly that this is about Overwatch, but I should be able to observe that that's what's happening and perform my role automatically. So I've been commanded, but I've been commanded at the more abstract level of, oh yeah, this is what we're doing now, rather than having a particular person tell me that that's what we need to do now. We're very interested in communication aspects. So one of the hard rules that we were given is, I don't want you to come up with some fancy workstation that somebody is heads down all the time and little joysticks and all that. We need something like that for maintenance. We need something like that for other things. But the most we'll let you do is a small tablet. So in case the robot wants to give you imagery, you got a way to see it. Or if you want to give directions by saying, go here, or take this path, you could do that. But we don't want you looking at that all the time. We would like to use speech. So the robot could get directions, I want you to go over there. The gesture is part of the speech. So where to go, or I'd like you to go to the building on the left. But some of this may require dialogue. If the robot sees two buildings, that could be the building on the left. It should be able to say which. So a genuine dialogue, but at a more abstract level than simple command. So we've been working on gesture-based control, things like facial recognition too. What's this person looking at? Are they alarmed? Did they just give me a nod? So a nod, yes, or I hit the yes button, or I say yes, or some other gesture should all be equivalent for the robot's purposes, the way it would be with a human. So recognizing these things on a mobile robot has been one of the issues. We have some advantages, though. I'm going to show you some gesture-based work where the gestures are actually from accelerometers. So it could be direct observation of the gesture, but it also could be remote. So I could do gesture-based remotely using a link. So, but the idea is natural gestures can be transmitted to the machine. So we're doing a lot of that. The really weird science, though, is social dynamics. This is non-team social dynamics. How do people in this culture behave? How do I read a stop sign in a strange foreign land? Who do I have to obey? So we're not talking combat here. We're talking about robots patrolling down the street, and a police officer does this. Should the robot recognize what that means? Should it also recognize that that's a police officer and it's something that should be obeyed versus the Taliban saying stop and we're going to disassemble you? So some low-level social things. Who should you obey? What are the cultural norms here? Which side of the street do people drive on? How closely can I approach somebody before they become uncomfortable? If my desire is to make them feel uncomfortable, that's a useful thing to know. And if my desire is to make them feel comfortable and basically ignore me, get comfortable with the idea of my presence, then that's a useful thing too. There's been some commercial spin-off of this. We did these studies with iRobot. They're building a robot that's going to be working in hospitals and the like. And the robot would, if it was in a hurry, push you out of the way in the hallway. We told them that would be not a good thing. So now it does the equivalent of a little nod. I see you, and I'm going to pull it aside. Yeah, question?
But should the robot be also aware that if you're bothering a human being, a lot of them are going to react to that thing. Like if you're going towards me, I can just kick you out of the way as well. Like if you're attacking me, I can attack you back.
Well, yeah. So this is basic research. This is signaling. Suppose your goal is to move a crowd from where they are to some other place, okay? And you have a group of robots and people who are trying to do that, all right? Understanding what would cause them to move, understanding how closely I need to be to my partners and how closely I should approach these to cause the motion can be very important. We foresee a day when these robots will not necessarily be in hostile environments all the time. They may be trundling down the road delivering a package to you. Maybe it'll be Big Dog delivering a box to your house or something like that. Okay, so understanding how to work with humans, not just as moving obstacles, but as sentient beings and doing appropriate things, including signaling them, I see you, or I recognize that you're doing that. So think, do robots need turn signals? Well, maybe, or maybe they need the equivalent of a turn signal, which says, here's what I intend to do. Or maybe it should automatically do it. So this is real basic research for a longer-term future. Question?
Do you enter ethics here in this part of the question, like not killing innocent people, not recognizing who's
We do a lot of human subjects work, and the simulation environment that's mentioned here is creating complex situations and having people observe and say, what's going on here? What's the robot trying to do? What are these people trying to do? So we're trying to capture how people interpret these things, and also then when we have the robot give these behaviors, do they correctly interpret as we expect? So these simulation environments, I mean, it's hard to build a real environment to do these. So the simulation environment might be you have a robot that's a guard of a place, and it moves around this virtual world, and you're observing it. What is it doing? Oh, it's patrolling the area. In one of the ones, for example, that we've run a lot of students through, the robot is patrolling in the distance, and suddenly somebody starts running, and he's got something under his arm. And the robot changes what it's doing and starts after him. What's the robot doing? What's its function? It's a guard. It's detected aberrant behavior, and it's pursuing. Okay. So having people be able to correctly, by observation, from the motions and actions, interpret what's going on is very important. So we have simulation test beds for the human element of that. We do auditory, visual, and tactile, but notice this is the modality, so sound. Sound doesn't necessarily have to be speech, okay? Remember R2-D2 and C3PO? Well, R2-D2 squeaks and makes beeping noise and so on, but people understand when it's worried, when it's happy, when it's concerned about something, when it's fearful, from squeaks and buzzes. And we do that with dogs too. Dogs don't talk, but we can read their emotion. Dogs are very clever. They've figured out how to stimulate our senses. And there's even a theory that dogs are parasites because they've learned perfectly how to evoke our sympathy so that we feed them, keep them warm, clean up their wastes for them, and so on. So I don't subscribe to that. I think they're very nice, but the dogs have learned to read our social signals, and we to read their social signals as well. Robots should be able to do that. We're interested in gait, gesture, distance, and so on. A lot of study going on for that. And we're using tactile because soldiers often use that. You saw the search and area. They use a lot of hand signals that involve touch. Silent conveys a lot of information, which way to go, what to do. And they use a lot of gestural signals. Speech is not good if you're trying to hide. Okay, so these other signals are used. But I'd like to point out that there are two different kinds of information you can get from this. There's explicit, go over there. And there's implicit, I'm concerned. I'm not sure. I'm in pain. That are implicit, and the robot ought to be able to sense some of that, because that has to do with the team behavior. Okay, can we recognize that this person is heavily engaged in something and is maybe not going to perform the function that I would really expect, so I can adapt to deal with it. So the implicit is sort of like getting a feel for what's going on. People are generally skilled at this. Not all people, but many people are. And the explicit. So we're trying to do both in these modalities. So among the things, yeah, question.
Okay. On the previous slide, you said that for the auditory, the only explicit example you gave was language. What about other explicit commands like clicking your fingers or making sounds?
Some of those are used too. We're not using those for human signaling to robots at this point, but the other way around. So the robot, if you give it a command and it just sits there, does it understand me? Is it going to comply? So how might it respond? Well, maybe a simple beep, maybe nodding a sensor. People automatically interpret that nodding of the camera as a yes or a no. So using some organic capability to give the equivalent of human signals is the basic idea. One of the goals is adding the least amount of stuff possible. So how could I repurpose these things in ways that people would understand naturally? So among the things we did was develop a squad-level vocabulary. So we went out to Fort Benning and we went to other places and worked with people and found out how they use words, among themselves, and what the shortcuts are that they use. And so that becomes a basis for vocabulary for a robot. So it's not a huge vocabulary. It turns out that people in these tactical situations don't use 10,000 different words. They might use a few hundred different ones in these situations. Another interesting thing about the squad stuff was that squads developed their own shorthand.
High-performance team.
Yeah, so they develop their own cues for things. And if you want the robot to be able to work with them, they have to be brought in on what this really means. A long time ago, when I was working in the AI lab, I found an interesting thing about hearing impaired. So when one of the things that, if you're using gestures, is they will define a global term. So the people who study history, let's say they're over there. So when they want to talk about people who study history, they point in the direction. They don't happen to physically be there, but I've defined a spatial position to mean that category. So once defined, then you carry on a whole conversation referring to whole groups by just where they are in some spatial sense. Robots should be able to do some of that too. Speech and gesture we've done. I'll show you a little clip of controlling Big Dog with hand gestures. Okay, and have been working to integrate the speech gesture into what's called the world model. So the world model that used to exist was all physical world, but now it includes cultural world, team members and other humans that might be in there, plus all these metaphors. You can imagine this may require a fair amount of computing power to do, so I think this is still exploratory development, but major steps. These cultural models that are still very experimental, we're going to continue to gather data because that will become important as robots work in domains where people will be present. So, closed loop communication. We want to actually have a dialogue, so we'd actually study dialogue. What does it mean for the robot to ask me a question? How should it ask it? Should it be verbal? One of the things it could do is say, I see two buildings. Which one do you want? And that could just be bringing up a picture with a question mark and two arrows, and you just say this one, or you say the one on the left. Work was done in my old laboratory on perspective taking, which is something humans do very well. Okay, if I'm facing this way and I say on the left, and you're facing me, it's not your left, it's your right. The vehicle ought to be able to understand that that orientation is relative to me and to the translation. Or you might be saying on your left, and then I've done the spatial, so it needs to understand that that's different. Or suppose I say, go to the red cone. This is examples that were done. The robot sees two cones, but knows that I only see one cone. My line of sight is such that there can be only one cone that I see or one building. So it doesn't have to say which cone. This will get into like comic routines, okay? It can infer with just a little bit of logic that since I can only see one cone, the one that I can see must be the one that I'm referring to. So this is all the perspective taking, and it's just one notch up in logic and capability, but a huge one for getting things done.
What about the other way around? What if a human can see two cones and I can only see one as a robot?
Well, then the human ought to be able to infer that too. But you could also query the camera and say, well, what does it see? Because I may or may not know what it can see. So that might be a dialogue and say, I see two, which is it? So not totally solve problems, but you understand the issue of perspective taking, and important to solve a lot of miscellaneous conversation that might otherwise be necessary. A lot of humor is based on those kind of misunderstandings. So the social dynamics, we have a whole simulation framework for doing this to try to understand how people interpret situations so the robot can make similar ones. So these are tools that are available for other people to use, and the role that we often play is, what's the human side of this? And we have large, so our simulation is human-centric. It's people, how people behave in certain situations, how they interact with gear. So a lot of this has to do, and I've often had a question, psychology students are required to participate in these things for class credit. Are they just fooling around, or are they doing this for real? So the mentality of psychology students may not be normal. Okay, just a conjecture. Okay, but the real question then is, so we often pay with gift cards. So we think to earn your gift card you may be doing, or we use ROTC or real Army people, or go in the field and do this to validate. So we run students first, but then we validate it, because we've actually had students fall asleep while operating a robot. They were so comfortable and happy and engaged, right? So we have to drop that data. And we're working right now on what this interaction media is. We're going to use a small tablet. But one of the rules is that they can't have the tablet out all the time. So we picked a tablet that would fit in an expansion pocket. It won't fit in this pocket because we need a little more space. But the goal would be that that actually could provide tactile feedback. If the robot understands, it might buzz twice. Okay, and you would feel that. If you needed to look at an image, you could. And for some route planning systems, if the robot says something's coming out of the building, maybe it's whispered in your ear, you could look and identify and decide whether that was good or bad. So the goal is this is available, but it's not your primary mode of interaction. This is also classifying people. The perception people have had an issue of it's hard to classify people. It's hard to track people, especially with not much computing power and low resolution cameras. So here's what we ask for. I want the following classification only: adult male, adult female, or kid. So just with those labels, you can infer a lot. If there's an adult male, an adult female, and kids walking together, that's probably not as threatening as a bunch of adult males approaching you rapidly. So even with just fairly reasonable classifications, there are a lot of inferences you could make that would be useful in deciding this problem. If it's a group of adult males with Kalashnikovs, that might be more alarming than shopping bags. So a little bit of additional information may be useful in making these things. So one of the goals is reporting what is useful to perception people. Perception people want to perceive everything and label it. But the question is, what's most important for problem solving? Yeah.
What do you use to separate males from females here? Because
dress,
in
clothing primarily. Yeah. In the areas that Arnie was primarily interested in, you can think burqas and other things as one way. But in our culture, you could do the same thing. Maybe it's hair length, maybe it's gait.
I mean, in Iraq, men could dress in women.
Well, that's if somebody is in a disguise, we haven't solved that problem yet. Mm-hmm. So we can't peer beneath the clothing. So, we'd be happy just to be able to classify these as people of a particular age or gender, if we could, or just people. Right now, in a static scene, it's just something.
Can I just throw in a comment?
Yeah.
Because I want to mention, like a scenario like that,
yeah,
or also your red cone scenario. I think when people justify and make the case that autonomous systems can work effectively, we should mention that some of these problems that can potentially be problems for an autonomous system, they're also problems for people. People can fail in this, and they do also. People can think if a guy wearing a dress, a person could think that's a woman. A guy following two cones instead of one, a person could go the wrong way there.
One big problem that roboticists have had historically is that people have a higher expectation of them than they do of people. They want perfect performance. So we want them to calibrate, not that this is perfect, but what it's good at and what it's not as good at. And people make these mistakes too. But if you'd like this to perform as a member of a team, it should have comparable capabilities to people. Maybe it'll have better in some respects, but that's something that would have to be learned. So I'm going to show.
A big problem with the testing is that there are not we test people non-deterministically. We get averages. We don't expect you to do every task exactly 15 seconds,
Well,
and
we
the
learn
Army's
who is
never
good at
come
what.
to grip with that.
In teams, we learn who is good at what, who's really good at this, who's not as
And
good.
about how fast, and about when
Yeah.
you're going to do this, and about, right. And that's been a major problem.
It is, and it's partly calibrating expectations.
Mhm.
Okay, so this is big dog and gesture-based control for big dog. The ropes are because they're afraid big dog might fall over, and because big dog is noisy, and so does an electric cable that powers them. So the idea is to be able to silently, or using, these are standard soldier signals, be able to command big dog or other robots. Turn around. In which direction? Turn around the other direction. Stop. Big dog's a little spooky. That is a manipulator. It's not a head. What do you think most people interpret that as? Okay. So that's gesture-based control for this. It could be verbal, and we'd like to be able to integrate that. It's actually done with an accelerometer on the wrist rather than visual. It could be visual. But an advantage of using non-visual is that you could do this non-line of sight as well.
Yeah, where are you going to put the camera to watch it? Yeah.
Exactly. Well, if it's organic to the vehicle, that's one thing. And Robin and I have talked about the idea of high cognitive architecture versus reactive control. And I'm a fan for robots, same as for people, pushing things down to reactive control where you may. Okay. So we've been playing around with reactive architectures that are team-like in performance. So little robots you're going to see are just little robots. We couldn't get the big ones. They wouldn't give us a whole squad of talons. Okay. So they move slowly. So it's not that this is slow computing. It's the vehicles are physically slow. But I'll tell you what's going on as we go along here. Wrong one? Yeah, good. That would be embarrassing. So this is multi-robots, and they're given some permission. So these robots are guarding that box. Their job is to guard the box. And what happens is if someone approaches, one of them, the one that's closest, is supposed to go out, and the others are repositioning themselves automatically to maintain surveillance. So, basically demonstrating confronting the intruder. This might actually have a practical application. Suppose you wanted to guard a warehouse, and you had 100 of these, and they all started approaching you screaming. Will that spook you? They're surrounding me. Okay. So this is true team behavior, because the robots monitor each other and what they're doing and understand that they need to fill in. There's no central control. They're monitoring both the external situation, the objective, and how to make this work. And this is the guard the warehouse thing. Their goal is to surround him and stay around him. So this could be guarding the queen, okay, but it could also be escorting the guy out of 7-Eleven who's threatening. So keep in mind that these are just slow. It's not that they're not capable.
I'm sorry, I have to go out and see
Okay,
for lunch.
just it.
Okay, what do you mean?
This is all done with something that has a terrible name, physicometric. So the rules all have to do with what you might call fuzzy logic sort of rules. How close should I get? How far can I get? Who should take this job on? There's no high cognitive. The high cognitive level could be used to help coordinate these sorts of things. So that's the basic deal.
What is mounted on those masts?
Hmm?
Okay. Well, what was mounted on the masts of the robots?
Oh, that's just a sensor, position sensor, and a camera. So we also have hand control based ones. So one of the things is rally, and they come around and surround you and then follow you around. So that's the very briefest of briefs on the human-centric stuff and what we're interested in robotics. and moving robots into the human inhabited world as potential partners. So what could you use this for? Suppose you have an elderly parent who you'd like them to be able to remain at home, but you don't want to hire an expensive home health aide. Could you envision building a robot that could serve as a surrogate pet, but had more cognitive capability, could remind someone to take their medication, could determine whether they actually went through the steps to do so? Did they go get it? Did they go through some motions? Could do a basic cognitive assessment. If you go in the hospital, they do a cognitive assessment. You know, hello, Mr. Smith, do you know who the president is? You know what day it is? What's your name? A robot could do that too and do a basic cognitive assessment in a pleasant sort of way. Carry on a conversation. So what would induce you to buy Grandma a robot? Would you trust it to be there? How confident would you have to be that it could actually do an assessment and call for help if needed? So questions for me? So dead silence. Yeah.
They were saying you envision a time in which they are not going to be like in a hostile environment all the time, right? But for example, in the first video that you presented to us, when the person was approaching the food box and the robots are commanded to keep him away, is there also a directive that he keeps on being stubborn, they have to attack or not?
Well, part of it is, what's the function of this? If the function is to help guide crowds out of a burning building, the robot might have to be assertive at a certain point. But what does assertive mean? Maybe approaching more closely or flashing a bright light or making a loud noise. So it doesn't have to be hostile in the sense of, I'll shoot you if you don't do this. It has to be able to apply appropriate social signaling. So if you were a human doing that, you might be pointing people. If they tried to break through, you might have to become more assertive. And so the question is, how would a robot do an equivalent thing?
And would you need to then either depend on the adaptability of the robot, or would you write like a set of instructions that it has to follow, or a combination of both?
We would like to have a basic procedure. So think about these squad tactics. You know, there are 27 of them, and they have different things. Who plays what role, and how do they do it? So in effect, that's a script. But the script is never perfect because conditions are never perfect. So the robot, just like people, would have to know which parts of the script are adjustable and which ones are not. So yes, there would be a list of steps you should take, but the robot ought to also be able to modify that to meet the end. Think service dog level 2. There's only so much you can do without deep cognitive models, but it can do a lot more than we do now with fully autonomous. So a basic script that you only follow that's what ants do. That can work great, but we have higher expectations for the robots we build. Another question.
I'm just wondering, like, you were saying that you wanted to kind of encourage, like, to a certain extent, the like anthropomorphizing of like what would, like, is that just like a trust thing? Is that why would that be beneficial?
Well, we personally don't want to anthropomorphize. We want to biomorphize.
Okay.
And the difference is this: we don't want it to be viewed as a person and has all the subtlety and capability of a person. So modeling dog-like behavior would be biomorphic. Okay. How can we recognize whether a dog is angry or not? Can we recognize when it's sad? Can we recognize when it's happy? Can we recognize when it's aggressive? When it's not aggressive? Well, yeah, we can. We can read those signals. Could you build similar signals in a robot so that people could, by observation, without special training, an LCD display that says, I am annoyed, could recognize that behavior? Could we make the robot acknowledge somehow that it knows you're there? So this thing's delivering medications down the hall. Could it look at you? And even if it's not actually looking at you, it points its screen to you and nods it. That, most people would interpret that signal meaning, I acknowledge that you're there. I know you're there, and I'm going to behave appropriately versus trundling along. Okay, so that's what we mean by biomorphic. The goal would be, with minimal training, that people can comprehend this at a more abstract level than it's just a black box. Okay, thank you very much.
Yeah, it's just, you've got a few more minutes,
okay.
but we're really running at the end of the time
Yeah.
that we normally allot for this, and I'm sure they've got students who want to stay and ask you more questions.
Sure.
So I want to make sure people that have to get to their classes have an opportunity.
All right.
Thank you. So do you have
thanks.
any final slides or anything? I didn't mean to just
No
like
more
to say
slides. That is it. The goal here is I could spend hours on any one of these things. The goal
Absolutely.
is check our website, check our clubs. If you want to learn more, come and visit us and work in specific areas.
Thank you so much. Let's thank our speakers.